Okay, so we've started recording again, and we're gonna take a pause from arc lengths. We're gonna jump back into cylindrical shells and at least do one example since the schedule called for it. And we're gonna work on this homework problem here. This is homework problem number 3. Let me think. We got different homework. Homework number 3. So we've got our degree 4 and our degree 2 curves up. Let's go ahead and graph those. And we're going to leave space above because we are going to rotate this about the line y equals 2. And so let's go ahead and make sure we're plotting our intersection points. And the general shape, at least, is going to be most important here. Then it looks like the graphs intersect that too. And so plotting these, we have our parabola and our quadratic. I guess I should say the quartic. Okay, so here's our graph, and of course we are bounded between these two curves, so we don't need any of the extra here. We wouldn't be between those curves, and those regions would be infinite. So of course, first step, you're going to want to set those curves equal to each other. Of course, you can see the points of intersection by a graphing calculator. You do need to show that analytically. So set the two functions equal to each other. Should be easy enough to solve for the intersection points in that case. And then we are going to revolve around y equals 2. So this whole structure is going to be rotated upward. So we have to reflect that. And looks like I need even more space upward. We're going to be going right up to the top there. And so we're going to have that point as the middle. We're going to have this point as the top. Our reflected parabola is going to look like this. And then our reflected quartic is going to look like this. And so the shells can be really weird to draw because the shells always start at the middle of the axis of rotation, meaning that if this is the area we want, then my drawings are not perfectly symmetric here. Let me try to make this a little better. Then our shells are coming this way. And the next shell, or other shells, will be coming here. And we're going to keep growing these shells. So these shells are going to start off long, then they're going to shrink, and then shrink to 0, but then the shells are going to grow again, and the shells out here are going to be wide again. They're going to be long. So our volume we are going to be integrating with respect to dy. And our area was 2 pi r times the height dy. Missed my r. I said it, didn't write it. So now we need
R2 minus y.
What'd you say?
Is R2 minus y.
Let's take a look. So 2 minus y was suggested for r. It is often the case where you want to do the axis of rotation minus y. So if we were to draw this out, our radius for a given shell is here. The distance from the x-axis is y. And of course, we know that that whole distance is 2. So yeah, our r, 2 minus y, what about our h?
Is it just the one function subtracted from the other?
Yeah. In this case, nicely enough, it's always going to be the right curve minus the left curve. And the green function, our parabola, is always on the right. So it's always right minus left. And so we can write this one as y squared over 2 minus your y to the 4th over 4 minus y squared over 2. So simplify that. Plug those two in for r and h. What are the bounds going to be?
0 to root 2.
0 to 2, good guess.
Root 2.
0 to root 2. Where'd root 2 come from?
Negative 2 to 2.
On root 2 by setting y equals 4 minus y equals, or y to the power 2, and set that to 0, and then solve for the y bound. If
Oh,
x is
shoot,
0.
yeah, I was just finding the y-intercept. Yeah, he's right.
Okay, let's go through the math. How do we find the points of intersection? We want to set the curves equal. We had y squared over 2 is equal to y to the 4th over 4 minus y squared over 2. So these are our intersection points. So you want to find the intersection points because those are what's going to determine the bounds. And so, of course, we get y squared is equal to y to the 4th over 4. So y to the 4th over 4 minus y squared equals 0. We factor out the y squared. And of course, we'll get y equals 0 and y equals plus or minus 2. So that's this intersection point, and that intersection point. Now, the bounds are going to be our y bounds, and they're going to be where the shells lie. You shouldn't have to do a whole lot of work. The bounds for the integral always depend on the region that you're integrating over. So we need shells from here all the way down here, right? The biggest shell is going to be like out here. And it's going to be all the way around.
So it's from -2 to 2?
-2 to 2, right.
Could we also just do 0 to 2 and multiply by 2, or is that not good in this situation?
No, I don't think that would work because 0 to 2, what is 0 to 2 going to give you? It's going to give you the shells from here to here. Sorry, let me move that. It's going to give you the shells from here to here, which even though the graph is symmetric beyond that, the shells are getting bigger. You're going to miss out on a lot of area, a lot of volume that's being obtained by these big surfaces of revolution. Yeah, and so again, our radius, biggest radius is goes down to -2, the y value, which will give us a radius of 4. And then we're actually kind of going upward, so we're shrinking, we're working inward. And then of course the smallest radius will be 0 right there at the center. Any questions on that? Okay, let's take a look at a few surface area, or not surface area, arc length examples. And we left off yesterday we know that our formula is going to be given by this. Which can also be written as this way, using Leibniz notation. And you can imagine if you have x as a function of y, just as we derived this, you could replace these with f prime of y dy if you are integrating with respect to y. And so we had an example of y squared equals x cubed from 1,1 to 4,8. So since we are on the positive side, y squared equals x cubed, graph looks like y is x to the 3/2. So it's got like a cusp. And it does something like this. So
Oh my god, yeah. Are you seeing the chat? They're also right. The instructions in number 3 tell you to go from with the region bounded by the x-axis, so it would be 0 to 2.
oh, okay. I didn't catch
Yeah,
that.
I noticed that yesterday. I tried -2 to the 2, and if you checked on Desmo using if you put integrate, it gives you 26 instead of 5.026 if you bound it from -2 to the 2. So it should be 0 to 2 instead.
Yeah, it does say above the x-axis, so we didn't even need to consider that second half, right? So I missed that cue in the instructions. Always read the directions carefully. So you're right. Direction or the integral should be from 0 to 2. Okay, so let me make sure I'm graphing this. X to the 3/2 should grow. I think I'm drawing it slightly backwards. I think we want to go this way. And we have a cusp this way. And since we are going from 1,1 to 4,8, we are only on this top half of the curve. So in many of these, like when we have a curve that's defined just as an equation of functions of x and y, you really have to determine which piece you are on, because we do, in this formulaic method, need either a function of x or a function of y. So when we solve this guy, y is equal to x to the 3/2, we should have a plus minus here The plus gives us the top half, the minus gives us the negative. So since we are integrating from, or traversing the curve from 1, 1 to 4, 8, we can use the positive one. And once we have that, we can compute our derivative. And now we just plug everything into the formula. We want to integrate 1 plus the derivative squared dx. And since we are integrating now with respect to x, we want the x coordinates that we are integrating in between. So fairly straightforward from there. Other examples in arc length. So in the homework, you guys have one. We can define functions in terms of integrals. So this will be related. I could define the curve itself as an integral. And we want to find the arc length from 1 to 4. So in all arc length problems, once you have your curve, so that might be our first step, like in the last problem, identify the curve, try to find y as a function of x or vice versa. And then compute your derivative. It's going to be the second step. So dy dx means we are taking a derivative of this guy. And by the fundamental theorem of calculus, that just gives us square root of x squared minus 2. And so our arc length, our integral is going to go from 1 to 4, since we're given the bounds, and we want square root of 1 plus dy dx squared. Which, nicely enough, when we simplify it, it'll give us square root of x squared minus 1. A little bit easier of an integral. So this one, of course, you'd have to do a trig sub, probably using secants, and then work out the rest. Other examples, let's do one with logs. Let's say we've got y is equal to natural log of 1 minus x squared from 0 to 1/2. And again, most of these skills come down to, one, identifying the curve, which oftentimes it's given as a function, remembering your derivatives, And then just making sure you're doing the algebra right when you plug it into the formula. So we'll have 1 plus this guy squared dx from 0 to 1/2. And then practice the algebra with rational functions, so we can go through that. You will see a lot of rational functions come up quite a bit. Dealing with this +1 under a square root, as we've kind of seen, can be tricky. Usually results in a trig sub. So if you have to do these by hand, you should expect that whatever integral results should be doable. So it's kind of always a good check that if you get something really nasty underneath a square root, check your algebra, check your work. So we want to simplify the integrand here. We've got 4x squared over, let's just write it as 1 minus x squared squared. We'll have to FOIL that out for the numerator. And we have to add 1 to that. So we want to combine our like fractions, or like terms in the fractions. So 4x squared, we will have plus 1 minus 2x squared plus x to the 4th. When we expand that out, all over 1 minus x squared squared. And so what do we get? We've got x to the 4th plus 2x squared plus 1 over 1 minus x squared squared. And now we want to be able to simplify this. If this was underneath a square root, we should be able to still integrate it. And at the moment, it doesn't quite look integrable. So you have to recognize that the numerator was cooked up in such a way that it is just x to the 4th plus 1. Excuse me, x squared plus 1, quantity squared. So essentially those same terms that we got when we expanded that square out, except we're changing the sign on the middle term. So it'll give us that plus. And now, nicely enough, when we put that, right, that was the term underneath the square root here. We'll have square root of, I'll just write it as 1 plus x squared squared over 1 minus x squared squared. The squareds go away. And we have something that looks a lot easier. How do we finish this guy?
Split the top portion of it.
Split the top portion of it. Probably going to be step 1. If you want, I guess you don't have to split the top portion of it yet. Then what are we going to do?
Partial fractions.
Partial fractions with this guy, yeah. And what's one of the problems with our partial fractions? The degrees of the numerator and denominator are the same. So you could do long division. You could split it 1 over 1 minus x and then x squared over 1 minus x, and then do the long division of x squared into that guy. Or you could just start with the long division. Or you can do some fancy tricks. Sometimes the fancy tricks work. Sometimes they don't. Let's try to take a look. Let's do this. So if you want to get around the long division when they're the same power, sometimes you can finagle the factor of the denominator in the numerator. What do I mean by that? I mean, it'd be nice if we had 1 minus x squared in the numerator. We have a positive x squared, but maybe I could write it as minus 1 plus x squared. But the numerator should have a constant of positive 1. So why did I do that? Well, I like this term because it's this term with a minus sign. So this is just negative 1 minus x squared over 1 minus x squared plus 2 over 1 minus x squared. Dx. So now our integral is just minus 1 plus 2 over 1 minus x squared. So it's a little bit of a shortcut getting around the long division. If we did long division here, we'd find that negative 1 as our constant term, and then this as our remainder. And then now, of course, you want to do your partial fractions. So 0 to 1/2. That integral, pretty easy. And then we've got, let's just write it out, a over 1 minus x plus b over 1 plus x. And then you got to do the algebra to figure out your a's and b's, and then integrate from there. Any questions? Do you guys want to see the rest of that? Question in chat says, why did we use the fundamental theorem of calculus in the last one? We use the fundamental theorem of calculus just because there are functions that we cannot define with a nice closed form expression. And by closed form, I mean written in terms of functions of x, like y as a function of x. There are functions that we have to define in terms of integrals themselves, right? So our function itself is defined in terms of an integral. If you take a look at the homework, you have a similar example to this. So I kind of wanted to just show that to you, that sometimes we do have curves defined in terms of an integral. It's actually kind of just in some sense, for these types of arc length problems, it's kind of like a workaround. It makes things a lot easier. Cooking up and thinking of these problems that can actually be done by hand, it's actually fairly difficult. And if you look at a lot of the book examples and a lot of the examples that do work, the functions that we can compute arc lengths for are going to be rational functions or functions with derivatives that end up having rational functions. Or like in the first example, we get these fractional exponents. You'll see a lot of these types of functions used in arc length calculations. And the difficulty is because we have this 1 plus a derivative squared underneath a square root. We've already seen how hard it is to integrate square roots, especially if there's wonky functions underneath. We can do quadratics reasonably well with trig subs, but even those can get hairy. If you have something like 1 plus x cubed underneath a square root, you can't integrate something like that. So in order to write problems, to do examples, to practice these techniques, the functions have to be chosen nicely enough with their derivatives that it will result in something underneath a square root that can be integrated. So one of the ways that you can kind of cook up easy examples in that regard is, well, if I define a function in terms of an integral, then the derivative of this function is actually the function we kind of want in some sense. So if you kind of have a little bit of foresight of what function do I want underneath this square root in the arc length formula, you can then create a parent function or a function, an antiderivative for it, simply by using an integral trick. Other questions? So for this last one, find your a and b using your partial fractions. Of course, the integrals of those should be pretty straightforward after you find those constants. The last thing to talk about in this section is the arc length function. And I'm not sure how much it's actually going to play a role. So maybe we'll just talk about it real quick. So the example, let's say find the arc length function. Of y equals x squared minus 1/8 natural log of x. Starting at the 0.11. So what is this function going to look like? Oh, this one's going to be weird to graph. So it's going to come up. We've got the 0.11. After the 0.11, natural log grows fairly slowly, and the x squared is going to mainly dominate the shape. The natural log grows slowly, so it'll decrease it. So it's going to look fairly parabolic, but maybe a bit wider. But then, of course, as x gets less than 1, this will get negative. And so it should blow up here at 0. Should look something like that. Again, graph it on Desmos, or use your Calc 1 skills and pre-calc skills to graph that a little bit better. We do know as x approaches 0, this is going to get to negative infinity, and so it should blow up to positive infinity. Where that exact minimum is, not sure, but not terribly important for the purposes of this problem. So as long as you got a rough graph, you're fine. And so what is an arc length function? An arc length function just means if I start here and walk along this curve, and we just want a function that represents whatever x value we specify, is where I want to stop. I know I want to start at 1. We don't know where we want to stop. We want to end at some x value. So we really just want the arc length as a function of x. So it's essentially the same process. It's just that our upper bound, we want to start at 1 and end at some arbitrary x value. We're going to use the same formula, just change the dummy variable. So the x from the function, let's just change it to a t. And go through those same calculations. So our y prime, if we change the x's to t's, looks like that. And if we want to do some of the scratch work on the side, sometimes I do that as well. Our y prime squared, or you can write it as f prime dy dx quantity squared. So we can do the squaring to the side if we don't want to write it all underneath the square roots. What are we going to get? So we'll have 2t squared minus 2 times 2t times 1 over 8t. So the t's will cancel out of that middle term, and then plus 1 over 64 t squared.
Shouldn't it be 4t squared, the first term?
Yeah, thank you. So t's cancel. What do we got in that middle term? We've got 4 over 8 So we've got 4t squared minus 1/2 plus 1 over 64 t squared. And now nicely enough, when we put that into our integral, yeah. The 1 and 1/2 are going to combine nicely. Oop, t squared is in the denominator there. dt. And what do we do from here? Now we can integrate. So we just get 4/3 t cubed plus 1/2. What did I do? I missed my square root. I knew I skipped a step. I'm like, there should be some factoring involved. Sorry, forgot my square root. We do need to factor this. So nicely enough, when the 1 and 1/2 combine, it just changes the sign on our constant term here, which essentially gives us the same factorization that we were just working with. So we get the integral from 1 to x square root of 2t plus 1 over 8t quantity squared. Squareds and square roots undo each other. And so now I just have the integral of 2t plus 1 over 8t dt. And then we'll have t squared plus 1/8 natural log of t from 1 to x. You do need to make sure you're plugging in the constants. It's not always going to be 0. So of course we're going to have x squared plus 1/8 natural log of x, and then some constant term. So it looks like minus just a 1 there. So our arc length itself as a function of x follows that guy.